took longer in California.
Yeah, that makes sense.
Is it longer? It is longer in California?
I mean, the potential part of it took me longer just because I mean I was going straight to school there.
Yeah.
So.
I don't know. Is there a reason why it's more?
I mean, because technically, right, if it's a public school, like taxes are going to pay that school. So, right, like my taxes or my parents' taxes, whoever's taxes, right, in another state weren't paying for that school, and so they charge you how much supposedly, you know, yeah, which is not anywhere close, but you know, that's fine. All right, welcome those on Zoom to our discussion on university tuition and how it's crazy. But, so, see here. Any kind of questions on anything before we get started today? Guess I'm not sharing the screen on Zoom, so let me share that screen here. All right. Okay, any questions anyone has on anything related with the course? Any questions here on Zoom? All right. So just a reminder of kind of the state things, right? Class-wise, a week from Wednesday will be the second exam, right? We'll cover everything we go over this week, as well as, you know, material we've already covered, right? Okay. Right, questions on the exam will be most similar to, you know, questions from like homework 3 and 4, right? You know, and then obviously questions we go over in class. You know, but again, there will be a decent amount of overlap with some things from exam 1, just because, right? You know, if you didn't notice, a lot of questions on homework 3 or similar types of questions that were on homework 2, you just had to calculate entropy and things like that, right? But you're still talking about expansions and compressions of gases and blah, 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 right? I believe I updated the exam solutions to the actual exam solutions. That kind of worked out. But if someone has tried to look at that and that's wrong, please let me know. Your homework is due Friday. I should have it graded for you by the following Monday, which will be a review for exam 2. So yeah, so that's kind of general class stuff. Right, again, as a reminder of what we've been talking about in class, right, the material, we've started off talking about these different thermodynamic quantities and discussing how we can calculate and describe changes in these quantities like internal energy and entropy and Helmholtz-free energy and enthalpy and so on. And then try to generalize these infinitesimal changes that we have, right? du equals dw plus dq or something like that, right? These small differentials, these small changes, to try to then generalize that to larger changes in the system, right? To then talk about different ways of expanding or compressing gases, talking about chemical reactions or phase changes and things of that nature, right? And how we can calculate these thermodynamic quantities for these different things, okay? And now we're starting to talk more about kind of the thermodynamic definitions of these phase changes, phase boundaries, and things of that nature. And we're going to start talking now about mixtures of things, and then mixtures and such, right? And discuss, right, mixing of stuff and the thermodynamics of that. And then that will lead to talking about, say, chemical equilibria and things of that nature, as well as then talking about electrochemistry and other such things. Okay. So, right, so we're using a lot of the concepts and ideas in these thermodynamic quantities that we've discussed before in these different applications and then mixtures of things, right? And applying these ideas to stuff that's a little bit more relevant to us as chemists than, say, expanding, compressing gases, right? Which has some relevancy, but not really as relevant as say talking about mixtures of things, right? And chemical reactions, and phase changes, and such. Okay. All right. So today we're going to talk about partial molar quantities. Yes, because when we're going to talk about mixtures, we're going to have to discuss these partial molar quantities, right? The first of which is partial molar volume. Okay. And why we need to talk about partial molar volume is because, right, so far, typically in chemistry, right, have people heard partial molar volume in other classes? Yeah? Oh, so, okay. All right. I did not know that. What, quantitative analysis or something like that? No. Okay. Right. But for the most part, right, we think of when we mix two things together, two solutions together, two liquids together, right, that the total volume is just the sum of the volumes of those two things. Okay. But that's not always true. Okay. Now, if I mix two containers of water together, then yeah, the total volume is just the sum of the two volumes of water. But if the two things I'm mixing together are not the same chemical compound, then the total volume is not the sum of the volumes of each of those containers, right, or each of those liquids, right? It's something a little different. Okay. And to discuss how we get that total volume and how we describe mixtures of these liquids and partial molar volumes. Okay. So, for example, right, if I were to add 1 mole of pure water to water, right, the total volume of water will just increase, right? So 1 mole of water takes up roughly 18 milliliters based off its density. Okay. And so, right, the volume will increase on that water container by 18 milliliters, right? And so the partial molar volume of water, right, of pure water is just 18 milliliters per mole, right, which is related with its density, right? The density of water is related with its partial molar volume, okay, for that pure water. But if I instead take that 1 mole of water and add it to ethanol, I will not get the same volume change, but instead the volume will increase by only 14 milliliters, right? And so this partial molar volume of water in ethanol is actually 14 milliliters per mole, right? So these partial molar volumes are something that depend on what you're adding to what, right? What things you're mixing together, right? And the kind of amount that you have of the, say, water versus ethanol. Okay. Right? And the reason why that total volume doesn't increase by 18 milliliters versus 14 milliliters, right, is because of the difference in the packing of, water molecules and ethanol molecules, and the difference in the intermolecular forces, right, for these molecules, okay? So, right, when you're mixing water with ethanol, water itself is, right, it, has a rough structure. Now, again, it's a liquid, right, it's a fluid, so it doesn't have a rigid structure, but, right, the water molecules are trying to maintain these hydrogen bonding interactions with other waters, right? And so there is kind of a rough structure of water, okay? At a very microscopic scale, you'll get clusters of waters kind of trying to form hydrogen bonding interactions as they're kind of moving around and such, right? Right, and the same thing with ethanol, right? That it has its own hydrogen bonding, right? Now it doesn't have the same structure, right, as water. Okay? And so when you mix these things together, right, what's going to happen is, for example, with this water, okay, the water, when it's mixing with other water molecules, ends up being a little bit more spacious, right, has a little bit more volume to it, because the water molecules aren't packing efficiently because they'd rather have these favorable intermolecular forces, right? Again, when any type of liquid or solid, right, its density, right, is related, I mean, obviously with its weight, I should say it's partial molar volume, right, because that doesn't depend on the mass of the thing, right, but the moles per volume, right, or volume per mole, right? So the partial molar volume of any liquid or solid, right, is determined based off of not only kind of the size and structure of that molecule, and then how they can pack efficiently relative to each other and what are their intermolecular forces, right? Because it might not be that the most efficient packing to take up the most, to have the least amount of empty space when stacking your molecules together is the type of packing that optimizes the intermolecular forces between the molecules, right? And so you have kind of this competing competition between how the molecules pack and then how their intermolecular forces want them to pack. And that can cause things to not pack as efficiently as they could, right? And so when you add, say, this water to ethanol, right, now there's these intermolecular forces with ethanol that the water's interacting with, right? And so typically, right, if I have, right, 18 milliliters of water in 1,000 liters of ethanol, right, I'm not really having water-water interactions here, right? It's going to be water surrounded by a bunch of ethanol, right? And that water surrounded by a bunch of ethanol happens to pack more efficiently than water surrounded by a bunch of water, right? And so that's why the total volume increase is only 14 milliliters, okay? Because now you've gotten the more efficient packing, more efficient, close interactions between ethanol and water than you do water with water, okay? So this is why, these volumes aren't necessarily additive, and why this partial molar volume of water, right, essentially how much space does 1 mole of water take up, right? That's the partial molar volume of water, right? How much space does 1 mole take up, right? Depends on what that water is interacting and surrounded by, right? If it's surrounded by a bunch of other waters, then it takes up more space than if it's surrounded by, say, a bunch of ethanol, right? And it's different than if I have a different solvent besides ethanol, right? Okay. The partial molar volume will depend on what things you're mixing together, okay? Right, so again, kind of that definition of a partial molar volume of some compound A, right, is just the change in total volume. I add 1 mole of A, some very large quantity of solution, okay? And again, that partial molar volume depends on the identities of the chemicals you're mixing together, okay? As well as the percent kind of composition, right? Whether it's a 50-50 mixture, 80-20, right? In the example I gave, right, like 99.99% and 0.01% or something like that mixture rate will impact what that partial molar volume technically is. And then thermodynamically, right, mathematically, if you will, right, that partial molar volume, V sub J, so we'll use this subscript J here, right? So like V sub H2O is the partial molar volume of H2O, right? Is defined as the change in the total volume divided by the change in the number of moles of substance J, say water, right? Holding temperature, pressure, and all other moles constant, right? So again, in these examples here, right, the volume of ethanol, like the number of moles of ethanol, the number of moles of this other, 1,000 liter water, right, will be constant when I add in this 1 mole of water, right? The number of moles of water in my solution of ethanol change from 0 to 1, right? But the moles of ethanol are staying constant, right? So all other moles are staying constant, besides, say, the one you're changing here, right? And then temperature and pressure are as well remaining constant in this mixture. Okay. Questions so far about what is partial molar volume, both its definition as well as kind of thermodynamic definition. All right. So the total volume change of any mixture, right, is related with right? Let's hold it over, right, with the change in volume with respect to change in number of moles of A times how many moles of A you've changed, you've added, right? Plus change in volume with respect to change in number of moles of B times number of moles of B you've added, so on and so forth, right? Which these are just the definitions of partial molar volumes of A and B, right? So integrating this out, right, you just get that the total volume is equal to the sum of the partial molar volumes of every compound times their number of moles, right? Okay. But again, these partial molar volumes are not some predefined number, right? It depends on the mixture you have itself, right? Partial molar volume of A and B depend on what the identities of A and B are, and then the relative amount of A and B that you have, right? So these aren't necessarily just some number, right? They can very much change. I'll talk about how they change as well. Okay. Right, and again, this is assuming constant temperature and pressure, right? So that your volume isn't changing because of temperature and pressure, right? Which we talked about, right? How volumes of liquids and solids can change with temperature and pressure. Those are related with some thermodynamic quantities. I don't happen to remember. Volume changes with temperature, constant pressure. The change in volume, change in pressure at constant temperature. Right, the isothermal compressibility and the expansion coefficient, right? Or how the volumes of a liquid and a solid change, the change in temperature or change in pressure, holding everything else constant. Now we're talking about how the changes when the temperature and pressure are held constant or changing the number of moles. That's related with these partial molar volumes. Okay. All right. So partial molar volume of substance J is what? Constant for a given substance, related with this derivative. The volume occupied by 1 mole of pure substance J, of molar volume of J with respect to temperature and pressure, and these two or more. We have 2 or more. So if people feel like 2 or more, which 2 or more? E and C here. Close. So C here is not quite partial molar volume, right? The partial molar volume of substance J is related with what is the total volume change in the solution with the addition of 1 mole of that compound, right? So the partial molar volume of pure J is related with the total volume occupied by 1 mole of substance J, right? If you're adding J into a solution of just itself, right? But in general, right, the partial molar volume is what is the total volume change with the addition of 1 mole of J into some large solution. So B is the only one that's kind of in general correct, right? But C here is sort of correct, but not in all cases, if you will. All right. Okay, right? So then we can ask ourselves questions, say like this, right? Right. So I have some solution where the mass of the solvent is exactly 1 kilogram, and I know the total volume of an ethanol solute water solvent, right? So I got 1 kilogram of water. Solution is given by this equation here, where B is the molality of the solution, right? Which is moles of ethanol per kilogram of water. The question is what is the partial molar volume of ethanol in a 0.1 molal aqueous solution. Okay. All right. Okay, right. So in the problem, given the total volume, right, with respect to molality, we're asked what is the partial molar volume of ethanol equal to, given the molality is 0.100. Just rewrite that. Moles, right? The mass is 1 kilogram. Okay. So what do I need to do to find the partial molar volume of ethanol? Say that again.
Find total volume by plugging the equation.
By plugging V into what equation?
B.
B. Okay. So if I find the total volume by plugging B in here, what would I then do to get the partial molar volume? Huh? I see. Okay. Huh, I see how you guys are doing this. Right, so right, what you're trying to do is essentially you're trying to get the partial molar volume as delta V over delta N, right? Essentially what you're trying to do, right? So the only concern with doing it this way, let's see here. Oh, is that a concern? I'm just trying to say the thing is with doing something like that, with how this formula is written, right? This is the total volume, which the total volume is equal to number of moles of ethanol times partial molar volume of ethanol plus number of moles of water, partial molar volume of water. So when I take that difference, yeah, try and decide if, I mean, you kind of make some sort of assumption that this is constant, essentially, in the problem, mainly that partial molar volume is constant. I mean, I guess I'd be curious to see what answer that ends up giving. Did you guys get a number in that way? Yeah, not quite. All right. Well, let me know. Get one. We'll see if that compares. Right. What is the thermodynamic definition of the partial molar volume of ethanol? Right. Yeah. Right. Change the number of moles of ethanol. Right. And so, right, which, right, these are basically kind of the same thing, right? This is talking about a large change, right? This is talking about some infinitesimal change, right? This is the slope, right? This is kind of, yeah. So again, right, this is basically kind of assuming, if you were to plot the molality, the number of moles of ethanol versus the total volume, right? This relationship, right? Because what you're doing is you're going from like 0 here, right, to whatever the number of moles in a 0.1, I guess this would be 0.1 moles, right? So 0.1, right, moles of ethanol, right? It has some total volume up here, right? And so you're taking the difference between these 2 points, right, to get the slope effectively at this point, right? Because that's, right, the partial molar volume thermodynamically is defined as the slope at this point at 0.1 moles, right? What is the slope of that total volume, right, with respect to the number of moles of ethanol, right? So if this happens to be a straight line, right, then that's fine. But if it's not, right, then it won't necessarily be quite the exact same thing, right? But it could definitely be very close. But yeah. So trying to do this, right, the main thing is, right, what is the volume in terms of moles of ethanol? So we can take that derivative, right? Right, and the molality, right, is defined as what? Yeah, moles of ethanol, right, over mass H2O, okay, which the mass of water is staying constant in this problem, right? And so, right, all of these B's I can just replace with this, right? So that I have partial molar volume of ethanol, ddN of ethanol, of 1002.93 plus 54.64 times N of ethanol over mass H2O minus 0.364 N ethanol squared divided by mass
H2O squared, okay, and plus 0.0283 moles of ethanol cubed over mass of water cubed, right?
Didn't quite give myself to put that all enough space to put that in one line with how large I was writing here. Right? But so I just got to take the derivative now of all of this respective number of moles of ethanol, right? So V of ethanol, right? Derivative of this, 0, right? And derivative of this term here, second term, 54.64, blah, blah, blah. Respect to the number of moles of ethanol. Yeah, 54.64, right? Divided by the mass of water. Okay. Then we minus next term, right? We'll have 2 times 0.364 number of moles of ethanol divided by mass of water squared. Okay. And then plus 3 times 0.0283 times number of moles of ethanol squared over mass of water cubed. Okay. This partial molar volume of ethanol, right? Then if I want to write it again in terms of molality, right? So using the fact that the mass of H2O equals 1, right? Kilogram or whatever, right? This is just going to be equal to 54.64 minus, what is that, 0.728 times molality B plus 0.0849, thank you, yep. B squared, okay. So this is the general expression, right? Using the fact that the mass of H2O, right, that mass of water is 1 kilogram, okay? So just plugging into 1 for all, right? Each one of these terms are kind of divided by the mass of water, so, right, dividing that out, right, gives us this term, right? So then plugging in B equals 0.100 into this above equation will give us the partial molar volume of ethanol, okay, which, right, so take the derivative, you get 50.57. Okay. Questions about that? I mean, I could have used the number of mole. I could have used N of ethanol and used the fact that the molality, right, since the mass of water is just 1 kilogram, molality is, right, tells us the fact that I have 1.1 mole of ethanol. So yeah, I don't need to go back to using B. I did that just because, you know, the original formula is given in terms of molality. So I don't know, I just felt like writing the next formula in terms of molality, but there's no particular reason why, right? I could have written it just in terms of number of moles. Okay. So, right. Now, it's not asking this problem, right? But let's ask ourselves, oh, what the heck did I just share? I have no idea what I just did. Portion of the screen. Okay, that was. All right, try that again. Right, let's ask ourselves, right, what is now the partial molar volume of water for this solution, right? Again, it's not asked, right? Well, we could ask, what is the partial molar volume of water, okay, in general, right? Any thoughts on what we might use?
Can't we just use that B equals NB plus NB?
Exactly, right? So this equation that we have written here, I'm going to rewrite it, right? Right, so the total volume, right, is just the number of moles of ethanol times the partial molar volume of ethanol plus number of moles of water times partial molar volume of water, right? We just found what the partial molar volume of ethanol is, and we're given total volume. So I can use this equation to solve for the partial molar volume of H2O, right? So the total volume, right, is, this 1002.93 plus 54.64b minus 0.364b squared plus 0.0283b cubed. That equals the number of moles of ethanol, okay, times partial molar volume of ethanol, which is 54.64, and I'm going to leave this mass of water, put this mass of water back in, so not using that. So putting back the mass of water, okay, and we'll see why in just a minute, right? Minus. Oh, yeah, sorry. Yeah, so I'm using the equation to find out what it is in general, I guess. 0.728 B over mass of water plus 0.894 B squared over mass of water. Okay. Right. And then that's plus number of moles H2O times partial molar volume H2O. Right. So, right, if I notice right, I have the number of moles of ethanol divided by masses of water in each one of these equations, right? It just means each one of these things is multiplied by the molality, right, of ethanol. And so this, right, and so I'll have, right, so kind of rewriting this equation here, right, this is just 54.64b minus 0.728b squared plus 0.0894b cubed, right? Okay. And so if I subtract this onto the other side, right, we see the 54.64b's cancel, okay? This will end up being a positive 0.364b squared, and then this will be a negative 0. Wait here, I'll write it out, right? So right, putting NH2O, VH2O, right, this will equal right, 1002.93 plus 0.364b squared minus 0.0, that multiplied by 2 here, 4566b cubed. Okay, so again, I get this line here, right? I get this line here by subtracting over, right? It took all of this and subtracted it on to this other side, right? So that 54.64b cancels with 54.64b, and and if you do the other math right, you'll get these values here. Okay. So then finally, to get the partial molar volume of water, right, just divide by the total number of moles of water, if you will, right? And so partial molar volume of H2O is just 1002.93 divided by the number of moles of H2O plus 0.364b squared divided by the number of moles of H2O minus 0.0566b cubed divided by the number of moles of H2O, right? And if I wanted to get a numerical value for this, right, I could then use the fact that the molality is equal to 0.1 for this problem, right? The mass of water is 1 kilogram, and then you just use the molecular weight of water, right, to convert that mass of 1 kilogram to moles of water, plug everything in, right, and we get the partial molar volume of water for this problem. Okay. Questions about this? All right. So the next thing we'll talk about for partial molar quantities, right, is your partial molar chemical potential here. Okay. So we've already kind of been talking about this chemical potential for a specific substance, right, is related with the change in Gibbs free energy over the change in number of moles of that specific substance, right, at concentration and temperature, and assuming all other moles are constant, right. Talked about this already with different phases, okay, right. Talking about kind of the chemical potential of the solid phase, liquid phase, gas phase, right? So it's the same idea where you're taking the derivative with respect to number of moles in that phase, okay? You know, here it's kind of more general, not necessarily just phases, but, you know, given chemical compounds, right? Okay. And so if we use, so this definition, okay, of what, okay, the partial molar chemical potential is, okay, right? You have the same kind of relationship, not written here, right? But the total Gibbs energy of a substance, right, is related with the sum of the partial molar chemical potentials times the number of moles, right? So go back here to this equation 2 here, right? Replace V with the Gibbs energy, and then replace these partial molar volumes with your chemical potentials. The equation is the same thing, okay? Right? And this is true for any partial molar kind of quantity, right? I wanted to talk about the partial molar internal energy or the partial molar Helmholtz free energy or something like that, right? And satisfy the same type of equation here, right? Where the total value is just equal to the partial molar values of some substance times its total number of moles added up, right, for all different compounds. Okay? Right? And so, right, given that, right, the change in Gibbs energy then can be related with the change in this sum of partial molar chemical potentials times the number of moles. Okay? But we also know from before, right, so from a couple of lectures ago, right, we wrote out the total differential Gibbs free energy is VdP minus S dt plus mu dN. Okay, I don't know if you remember that equation, right? But it'll pop up again different times, right? But the total differential Gibbs free energy, right? We can write it VdP minus S dt plus some I of mu I d and I, right? This is that change in Gibbs free energy, right? This is before we started talking about partial mole quantities, before we talked about mixtures, right? When we were just talking about kind of definitions of Gibbs free energy, trying to derive its total differential and things like that, right? We had a similar type of equation for, say, internal energy, that fundamental equation. Oh crap, I can't remember now what it was like TDS, minus TDS plus PdV plus sum over I mu I dN I think was something. I think this was maybe the fundamental equation. I could be wrong. There might be like a minus sign I'm off on or something. Oh, okay, so that's positive and that's a minus. Okay, so right. So, but again, right. So we have this relationship, right? And so, assuming constant temperature pressure conditions, right? Then this change in Gibbs free energy, right? This goes to 0, that goes to 0 because temperature and pressure are constant. I'm just left with this sum over mu sub I dN sub I. Okay. And so both of these equations 1 and 2 have to be true, that the change in Gibbs free energy is related to the change of the sum of mu sub I times n sub I, but the change in Gibbs free energy is also related to the sum of mu sub I d n sub I. So if you factor out, kind of do the chain rule or product rule or whatever it is, right? For this change, right, this is d mu sub I times n sub I, and then mu sub I times d n sub I, okay? The result will be that sum of n sub I times d mu sub I has to equal 0, okay? Right, so for a given, say, for a binary mixture, right, number of moles of A times the change of the chemical potential of A plus the number of moles of B times the change of chemical potential B has to equal 0. And this is true in general, and this is related to the Gibbs, this is called the Gibbs-Duhem equation, okay? Which again says that, if I have some mixture, something, and the chemical potential of one species changes, I have to have a change in chemical potential in all other species accordingly, since the sum of the number of moles times those changes in chemical potential equals 0, okay? And this is going to be true, right, for any of these kind of partial molar values, including, say, partial molar volume that we just talked about, right? So that the sum in the change in number of moles of J times the partial molar volume, times the changes in partial molar volume of J equal 0, okay? So this is true for any partial molar quantity, okay? This Gibbs-Duhem equation works for any of them, okay? Right? Which says then that, say, for partial molar volumes, right, that if I have an increase in the partial molar volume of substance A, that means the partial molar volume of substance B has to decrease, okay? Right? Because if I have a binary mixture, right, if the partial molar volume of A were to increase, partial molar volume of B has to decrease, such that the sum of those two changes has to equal 0, right? And so you see here in this relationship, right? So this is just applying that Gibbs-Duhem equation, okay, to relate the partial molar volume of water to partial molar volume of ethanol, okay? And we get this thing, right, where you see the partial molar volume of water as it increases, the partial molar volume of ethanol decreases, and then vice versa, right? As ethanol increases, water decreases, okay? Now the slope of these things are different, and that's because, right, these changes in partial molar volumes are multiplied by the total number of moles, okay? And here the x-axis is the mole fraction of ethanol. So when I have very few moles of ethanol, right, in order to maintain this equality, right, the number of moles of ethanol is very small, and that change in partial molar volume of ethanol has to be very large, okay, compared to the change in partial molar volume of water, when the number of moles of water is very large, right? So you have more gradual changes out here for water, and then you get more drastic changes, right, when the number of moles of water starts to become very, very small. And then the vice versa effect here for ethanol, where you have much larger changes. You have few moles of ethanol, and more gradual changes when you have a very large number of moles of ethanol. Okay? Right, and these relationships between partial molar volumes, right, of water and ethanol, right, this can be experimentally derived and shown, right, that this holds true, that this Gibbs-Duhem equation is in fact true in general. Yeah. So yeah, so if they're equal number of moles of the two, then yeah, the change in partial molar volume here is going to be equal to opposite sign of partial molar volume here, right? So if you kind of looked at the slope of the partial molar volume of ethanol in kind of this region and the partial molar volume of water in this region, you'll see that they're pretty close to each other. Yeah. Other questions? This Gibbs-Duhem equation. Right. So if I add sodium chloride to water, its partial molar volume increases. What happens to the partial molar volume of water? It also increases, it decreases, remains the same, or need more information. It will decrease, right? Because I have just a solution of water and sodium chloride. So so it's a binary mixture. So if the partial molar volume of one thing increases, partial molar volume of the other thing has to decrease, right? Right, and we know that because that Gibbs-Duhem equation, right? So B here, it decreases. Okay? Which of the following equations is not consistent with the Gibbs-Duhem equation? So yeah, C, now it's not consistent, not just because it's something we haven't seen before, but C is not consistent because temperature is not some sort of partial molar thing. Okay, there's no partial molar temperature. Okay, right? You can't, yeah, there's just no such thing as partial molar temperature. Okay, that's not a thing, doesn't exist. Yeah.
Also, for the Gibbs-Duhem, I think it's
Yeah, I guess we did for all of those. We had a constant temperature. I'm trying to think if there's one where you don't have to assume constant temperature, right? So we assume constant temperature and constant pressure, right, when we kind of derive these things. But I don't think you necessarily need to assume that. Like it could be constant other things besides just temperature and pressure. Right. Yeah, I'm just trying to think of other things. Yeah. I'll have to look more than that, look that up to kind of decide if you have to assume temperature is constant. I feel like for equations A and B, we did use the fact that temperature is being held constant to derive those, and so that's true. But there might be some other Gibbs-Duhem type equations where temperature doesn't need to be assumed to be constant for those to be valid. But I can't think of it off the top of my head, so I'm not. Yeah, I don't know. I guess I wouldn't be shocked if it exists. So I'll have to look that up and get back to you on that. Yeah. Other comments, questions about this question? We can see here it's not something consistent with the Gibbs-Duhem equation. Okay. All right, so let's do a problem applying that Gibbs-Duhem equation. Okay, so here I'm given the partial molar volume of K2SO4, right? By this right equation here, and where B again is the molality of our solute K2SO4. The question is, what is an expression for the partial molar volume of water for this solution? Okay, given the fact that the molar volume of pure water is 18.08 centimeters cubed. So I think for time, I'm going to start writing some things down. Okay, so this is basically what we're given in the problem, right? Partial molar volume of K2SO4, right? B, here's the molality, right? Given the partial molar volume of pure water. And the question is, what is, in general, for this solution, the partial molar volume of H2O, right? In terms of the molality of the solution, okay? And so what might we need to try to use to find that partial molar volume of H2O? What relationships do we know that relate the partial molar volumes of different compounds? All right, so we got the Gibbs-Duhem, right? We also know kind of what we had last time, right? V of K2, right? V total volume is number of moles of K2SO4, and partial molar volume K2SO4. plus moles of H2O, volume of H2O, right? We know this relationship, okay? Now we don't know what the total volume is and things like that, so we can't really use this. But we also know, as mentioned, right, that Gibbs-Duhem equation, right, that the number of moles of K2SO4 times the change in partial molar volume of K2SO4 equals number of moles, I'll put a minus sign out here, number of moles of H2O times the change in partial molar volume of H2O, right? This Gibbs-Duhem equation, right, is the sum of these two things equals 0. So let's just subtract 1 on to, say, the other side, right? So number of moles of K2SO4 times change in the partial molar volume of K2SO4 equals number of moles of H2O times change partial molar volume of H2O. Okay? Right, so this is our Gibbs-Duhem equation. Okay. All right. But in this equation here, right, I have a relationship to change in dH2O, change in dK2SO4, okay? Right, but I want to know what is the like total, right, partial molar volume of H2O, okay? Now, to get that, right, I can look at this equation and say, oh, well, if I were to somehow integrate out this change in partial molar volume of H2O, right, from its pure value, right, assuming a molality of 0, right, to some mixture, right, which is what I'm looking for, right, and then I could potentially get my answer. But problem is I don't know, right, what is this quantity here in general, and say what are the moles in terms of like these changes, right? But what I can do, right, I can look at what is the change in the partial molar volume of K2. Why do I keep on writing H? I don't know. I guess I'm talking about acids and bases in general chemistry, so I'm often writing H2SO4 instead of K2SO4 here. So I just, yeah. K2SO4, right, with respect to the change in number of moles of K2SO4, right? I can calculate this, right? And we'll see in a second why, right? But so if I calculate this, right, this first term is 0, because, right, the derivative of the constant is 0, and this is going to be plus 18.216 times 1/2 times 1 over mass of H2O to the 1/2 times then the number of moles of K2SO4 to the minus 1/2, right? The derivative of x to the 1/2 is 1/2 times x to the minus 1/2, okay? But here I'm taking the derivative with respect to number of moles of K2SO4, okay? So this mass of water is just a constant, and so I just got to pull that out, right? Because again, the molality B here is the moles of K2SO4 divided by the mass of water, okay? Right, so this tells me, right, so this is this derivative of K2SO4 with respect to the number of moles of K2SO4. And then if I just multiply both sides by the change in the number of moles of K2SO4, I get that this change in the molar volume of K2SO4 equals, that divided by 2 here, 9.108 divided by the mass H2O to the 1/2 power, right, times 1 over number of moles of K2SO4, right, to the 1/2 power, right, times the change in number of moles of K2SO4, okay? So now, right, by taking this derivative, right, what I've found is I found this relationship between how the partial molar volume of K2SO4 changes with a change in number of moles of K2SO4. And then I can use this relationship to plug back in up here so that what I have, here's the change in the partial molar volume of H2O times number of moles of H2O equals minus the number of moles of K2SO4 times in this change in partial molar volume of K2SO4, which happens to equal 9.108 divided by mass of H2O to 1/2, right, times the square root of the number of moles of K2SO4, okay, times in this change in number of moles of K2SO4, right? Which now, right, this is a kind of a differential equation here that's relating with the partial molar volume of water to some change in number of moles of K2SO4, right? So this equation I can integrate from, say, having no moles of K2SO4 to some final number of moles of K2SO4 at a molality, right? That will give me a molality B, right? And so I can take this differential equation here, right? And I can integrate both sides, okay? So on the right side here, I'm integrating my number of moles of K2SO4 from some zero number of moles to some final number of moles of K2SO4, right? And on the left-hand side, right, the partial molar volume of water at no moles of K2SO4 is that partial molar volume of pure water. And then I'm integrating this to some final partial molar volume of H2O, okay? And so the left-hand side here, I'm just going to have the number of moles H2O, okay? All right, because what's changing here is the moles of K2SO4, the moles of H2O are staying constant, so that just pulls out. So this is the partial molar volume of H2O minus partial molar volume of H2O, pure water here. And then now, okay, here I have NK2SO4 divided by NK2SO4 to the 1/2. So it's just NK2SO4 to the 1/2. So the integral, right, so this is the integral of x to the 1/2. Okay, which integral of x to the 1/2 is equal to what? It's 2/3 times x to the 3/2. Okay, so this is going to be, so there's a minus sign here that's still stuck around. So this is going to be integral. This is going to be 2/3 times 9.108 divided by the mass H2O. The 1/2.
Oh, why did you get 2/3?
So, right, so the integral of x to the 1/2, right, is equal to 2/3 x to the 3/2, right? Because the derivative, right, d dx of x to the 3/2 is equal to 3/2 times x to the 1/2. Okay.
Okay, yeah, I just forgot that you canceled out the bottom one, or the denominator earlier.
Oh, yeah. So sorry, right here, I kind of skipped a step, right? And I said, right, number of moles of K2SO4 divided by number of moles of K2SO4 to the 1/2, right? It's just equal to number of moles of K2SO4 to the 1/2. Yeah, so I kind of skipped a step here. So yeah, sorry about that. Yeah, I skipped a step, right? I took, right, this and this, right, and simplified it. Okay. And then this is left with number of moles of K2SO4 to 3/2, right? Which again, right, I subtract off 0 here, whatever, right? And so what I'm going to do now is the number of moles of H2O is just related with the mass of H2O and using the molecular weight, right? So we got moles going to mass. So grams per mole. So multiply by the molecular weight here. So let's see here. So number of moles equals the mass divided by the molecular weight, right? Yeah. Right. So here I'm going to take this number of moles and I'm going to convert this to the mass of H2O divided by the molecular weight of H2O. Right. And this times VH2O minus VH2O star. Okay. Right, and this is minus, I have no idea what the heck 2/3 is of that, but 2/3
9.108 divided by mass of H2O to 1/2 times NK2SO4 to 3/2. Okay. So why I did that is because now I can divide the mass. Well, I mean, so I'll multiply both sides by the molecular weight of H2O and divide by the mass of H2O. Okay. And what that will do is I'll then get the mass of H2O to the 3/2 here on the right side. And then I have the number of moles of K2SO4 to the 3/2, which means I just have the molality to the 3/2, right? And so this V, running out of space, right? So VH2O minus VH2O star equals the molecular weight of H2O, okay? I'll just use that H2O right before plugging it in, times minus 2/3 times 9.108 times the molality to the 3/2, right? So I got the molality to 3/2 because I took the number of moles of K2SO4 to 3/2 divided by the mass of H2O to the 1/2 and then divided by the mass of H2O, right? By bringing this H2O over to the right-hand side, you get that molality to 3/2, okay? And so, right, I can plug in here, right, the molecular weight of H2O is like 18, like 0.0 something, but roughly 18, right? You want to be more precise, it's like 18.0 something, right? Looking at here. Right. I think roughly 0.2 if you round it up there, maybe. Right. So plugging in the molecular weight of H2O here, 18.02, right? And so you go 18.02 times negative 2/3 times 9.108, right? Times b to the 3/2, right? And so then finally, the final molar volume of H2O, right, is equal to, this 18.02 times minus 2/3 times 9.108 b to 3/2 plus then this 18.08, which is the partial molar volume of pure H2O, right? So very top here, right, we're given that the partial molar volume of pure H2O is 18.08 centimeters cubed per mole. So plug that in there, right? And that's that partial molar volume of water. Just go to what those numbers are if you plug them in real quick. Right, so all of this, so on the slides, which are already posted online, right? Right, all this kind of detailed integration, things like that is also worked out there. Okay, get, this equation here that we had, right? Again, simplifies down to the molality to 3/2, right? And so yeah, plugging everything in, you get that the partial molar volume of H2O is 18.08 minus 0.109 b to the 3/2. Okay. Right, and so that is the partial molar volume of water for the solution, right, given some molality B. Okay. And so this problem is the one and only problem, I think, in this class where we do any type of integration. I'm trying to think if you guys have done any other. Oh, well, no, that's not true. I guess these expansion coefficients and things like that, you've done some potential integration with. But this is, yeah. I guess I feel like these partial molar volume questions are the ones that involve kind of the most kind of tedious math and things like that, with some derivatives and some integrals and things of that nature. But the two examples we just did today are the two questions one can ask for partial molar volumes, right? There's no other types of questions one can present besides, either here's the total volume, what is the partial molar volumes, right? Or here is the partial molar volume of one compound, what's the partial molar volume of another compound, right? Those are the only two questions you could ask for some sort of binary mixture, right? Okay. And so, right.
And I believe that there are questions like this on the homework as well for you to get more practice with it. Okay. The questions about what we did in the example problems here, and I think, yeah, I was going to say, I don't think I have any other examples worked out for today, right? But any questions about this example? Again, I know there are quite a few kind of steps here, okay? But again, the idea in this problem, right, is the relationship we had, okay, was this Gibbs-Duhem relationship, right, which talks about how the change in the partial molar volume of water is related with the change in the partial molar volume of K2SO4 times these number of moles, right? But I don't really, right, I don't know off the top of my head what that change in the partial molar volume of K2SO4 is, okay? But I'm given the partial molar volume of K2SO4, so I can relate the change in the partial molar volume of K2SO4 with the change in number of moles of K2SO4 by taking the derivative of this, right? So that's what we do here. We take this partial molar volume of K2SO4 and take the derivative of that with respect to the number of moles of K2SO4 to get this relationship here, right? Which tells me how the partial molar volume of K2SO4 changes with some change in number of moles of K2SO4, okay? And then I can plug that into this Gibbs-Duhem relationship, right? To relate then to how the partial molar volume of water changes with some change in number of moles of K2SO4, right? And then, right, I'm just integrating that out from having no moles of K2SO4, right, and having pure water to having some number of moles of K2SO4 and then having the partial molar volume of water in that mixture, okay? Right, and then after that, it's just, right, doing that integral and simplifying things down to get eventually that final answer, okay? The questions? All right. So on Wednesday, right, we will talk about ideal dilute solutions, right? So wait, is that Wednesday? Yeah, I think we'll talk about that and thermodynamics of mixing. And then Friday, I'm trying to remember. I recorded the lecture videos on Saturday for this week, and now I can't remember. But whatever. I guess I can just look up on the syllabus, right? So I have to guess. Right. So, oh, okay. No. So we'll talk about thermodynamics of mixing of gases and things like that on Wednesday, and then we'll talk about ideal dilute solutions on Friday. And that will be it for the topics that are going to be on exam 2, right? Oh, no, that's not true. We will talk about colligative properties on Friday. I was going to say, I swear we did colligative properties, right? So the plan is actually, yeah, so tomorrow, Wednesday, thermodynamics of mixing and ideal dilute solutions. And that quick, for some reason, is a tongue twister for me, right? The topics 21 and 22 we'll talk about on Wednesday. And then topics 23, colligative properties, we'll talk about on Friday. Okay. So we'll get up through colligative properties for exam 2. Okay. And so yeah, so exam 2 will cover up to topic 23 in the syllabus. Okay. And then starting after exam 2, right, we'll talk about activities of solutions. And that will eventually lead us to 2-component phase diagrams, talking about those. I'll talk about distillation processes and other things of that nature. And then finally, we'll get to chemical equilibrium and electrochemistry to kind of wrap up the semester. Crazy to think we're getting that close. Right. Like basically, this month in November, right? Okay, so I will see you guys on Wednesday. Again, get going on that homework if you haven't started it already. It's going to be due Friday.